Okay, welcome everybody. Welcome back to System Software. So last week we went over LLVM's compare and branch statements, which can be used to implement simple C's if statements, or C's if statements, or Java's if statements, right? Whatever language where we have this structured control flow, we can implement that using just compare and branch statements in LLVM. And today, project 2 was due. I think, so who turned it in? Did everybody turn it in? Oh, pretty good of the people who were here. The majority turned it in, that's pretty good. Okay, but you know, you have the late policy, so at your discretion, or whatever works for you. And so today, project 3 is sort of officially announced that project 3 is starting, although we've been talking about control flow and the grammar for the past week or so already. And yeah, the project description is here. We've gone over the grammar for this already, I think at pretty good length. So questions about the project 3 grammar?
Okay. So for the 4 if statements and the dangling else problem, when I read an if statement, I read it as whatever the single line right underneath it is what's executed if or not the conditionals meant. That when we were drawing up the trees, it kept going until we found it was matching. And then we also have the curly braces, and like, so where are we drawing the line on how that's being read in simple C?
Okay, so it's sort of a number of questions. How is the sort of how do you define what the body of the if statement is, and how do you know where the else statement matches that? If it's there at all. Okay, so these are sort of 2 distinct questions. Did you have a?
I just have a question as well. I'll wait until
Okay, so let's go over this first. I think it's an important question. So I didn't go into too much detail about how this sequence of 0 or more statements surrounded by curly braces works. So the way this works, at least in C and other languages like it, is that the curly brace is not part of the if statement production. So you notice that this if statement is actually pretty simple. There's only 2 child nodes that this if statement has. It's the expression node and the statement node. And as you may know in C, if I write an if statement in C, typically you will write something like this, right? You have curly braces. There's all sorts of flame wars on the internet about whether to put the curly brace here or here. Kind of a which side of the bread is buttered kind of argument. Not really, as you now know from parsing and generating code, that it has absolutely nothing to do with the final compiled binary, like literally nothing. It's equivalent to this program and this program. It's more readable. Okay, yeah, well, we can get to ideological arguments.
I feel like when you try to see, like many people, like their code doesn't compile because of 1 curly braces, and it's easy if you have it in the new line.
It could be. I mean, I understand English as the best language, so I could say English just happens to be more understandable. I don't know if I can really prove that that's true. I think it's more like what you're used to. It would be interesting if somebody actually came out with like a psychological study to say like this actually is categorically better, but I think that's a pretty tough thing to prove. At least from the programming language perspective, there's really no, I mean, this is all a design choice by the program language designer. And so, yeah, when we sort of learn C and we learn about these if statements, we think of this curly brace as being part of the if statement. But in the definition of the language, the curly brace is actually just a different kind of statement called a compound statement. That's why you can write something like this in C. So you guys have written code like this, right, with no curly braces. That's valid because the syntax for an if statement in C, as it is in simple C, is very much something like this, where what's after the conditional expression is just offloaded to whatever statement is. So just this is the way this recursive definition of languages works. We just say, well, I don't care what it is. I just know it's some kind of statement. And that's why when you write in C at least, you can organize the white space of this however you like. And you can even not have curly braces because curly braces is just a different kind of statement. That's reflected here. You can see that, so I didn't name it a compound statement, but in C this would be called a compound statement. You can see that the compound statement is at the same level as an if statement. It's like, if anywhere where you can have a statement, so for instance, in my program I can have a statement. Anywhere I can have a statement, I can also have a compound statement. That is curly braces surrounded by, curly braces surrounding a list of statements. So for instance, in C, if you want to get really readable, I can do this in C. This is totally legal in C. I can compile it in case you're not convinced.
But why?
But why? Why not? Well, in C at least, our language, we don't really have these same scoping rules, but I could do something like this in C. I could do that. So what happens? What's going to happen here?
I mean, it seems like 2 extra curly braces. Isn't it supposed to be like they're like extra curly braces and give you a warning?
Well, I'm going to get some kind of error. But the error is that, well, I should make this clearer here.
The int x only applies inside of those curly braces.
That's right, yeah. The curly braces, a compound statement, in addition to being a nice little notational convenience, it defines a new scope in the language. So we'll talk about that a little more when we get to functions for our next project. But I made the scoping rules for simple C very simple. We don't have nested scopes in simple C. But just the same way that I could write a while loop, I can write a while loop, and this seems totally reasonable, right? Like I can define x here inside of the while loop. And I mean, you guys all know this, right? That x is now local to the while loop. Who was familiar with this? Was everybody familiar with this? Okay, good. So you learn that you can have these nested scopes. And the scope just means the static sequence of code, the actual like text of the code in which that symbol can be used. So we'll get this a little more when we talk about functions. So that's kind of a preview. But the rules, the semantics for these compound statements says that between these statements, you have a scope. And that means any variables declared within that scope can only be used within the bounds of those curly braces. So even though this statement seems a little like odd, like why would you need to do this? I'm actually guilty of doing this before. I mean, I've actually done this before for kind of hacky reasons where I don't want the scope of this variable to be outside. I don't know if that's actually good practice to do that, but I've done it. It might be a little hacky. But yeah, this is totally valid because a compound statement is the same class as any other statement. Just like I can write a declaration of x here, I can also write a compound statement. Just like I can write a print statement here, I can also write a compound statement at the same level because they're all just statements. They're all just different variations of statements. Okay, so will this program compile? Who says yes, will it compile? Who says no, won't compile? Oh, okay, good. Why? Why won't it compile?
Because
Go ahead, call
Doesn't
it.
exist.
Yeah, this x doesn't exist. Yeah, and we're going to get that error because these x's were only defined under the scope, which is defined by the compound statement. And you have basically the same idea for functions, where the parameters inside of a function are just local variables, effectively local. They're a special kind of local variable, but they're local variables, and they're valid within these braces. So actually, the original K and R, the Kernighan and Ritchie, or Kernighan and Ritchie C. Let's see if I can find this. There was actually a different syntax for function declaration. Oh yeah, this was it. So this was actually I think the original, or one of, before the standard ANSI C. This was the syntax in C where you'd have the names of the parameters in the function, and the types were some sort of floating here. Just a different syntax. I mean, it means the same thing, but they kind of look like they're at the level of the scope of this compound statement after the function. So what if I do something like this? Think that's valid C? So this is not, I mean, this is not something you can like prove. I mean, this is like a design choice by C. So let's find out. Nope, it doesn't like it. Does not like it. Actually, it asks for declaration specifiers, which is interesting. But anyway, yeah, so this is just a design choice in the syntax of the language. So for functions, functions have to be followed by the function prototype, you might say. You know, the declaration of the function has to be followed by a compound statement. But that's just the rules of the language. There's no right or wrong here. In fact, there are languages where you can define a function without using a compound statement, like functional languages will do this if you're taking programming languages in Haskell. Okay, so that's all about curly braces and compound statements. Yeah?
I have a side C back.
Sure.
You can do generics in C by casting a double void pointer. It's a really hacky workaround.
You can do generics in C
by...
by...
has generics for data structure, you have a binary search tree, it can be index or string, like int or string.
You mean like a function pointer?
No, it's a double void pointer, and it doesn't take, it could take in any struct as a data type. It's really hacky also.
But it's a pointer to a void, a double void? You mean like this?
Yep. Oh, really hacky, I can send it to you.
You could just subvert the type system, right? Like you can, yeah, I think I showed an example of this with type checking, right? Where I could convert an int pointer to a float pointer. What's that? Yeah, it's just because C allows for some type unsafe programs. And the argument is for, you know, some systems programming in some cases where you may not know the type or you want to dynamically define the type. But yeah, you can certainly subvert the type system. I don't know if you'd really call that generics because it's not really checkable. Yeah, it's like poor man's generics. Poor man's generics, yeah.
In project 3, if we had an if statement, is it possible for the if to be followed by just a single statement without curly braces?
Yes. Well, let's look at the grammar to answer that question. So my if statement says if L paren expression R paren statement. So what can statement be?
It could be any of those others.
Any of these other options. So we could have, well, now let's switch to simple C. I could certainly have this in simple C, or this, because, you know, you can have any amount of spacing you want.
Okay, so
Or
with the expectation that it might not be followed by a curly brace.
Yeah, and it's if you're converting this grammar kind of, so now we don't have the problem of left recursion or anything. So you can almost make like a fairly faithful mapping from this grammar to a recursive descent parser. And I'll show the pseudocode for code generation today. But you can almost just literally say, I have a statement function. If it starts with an if statement, then I just read if, I read L paren, I read expression, I read R paren, and then I call the statement function. And you can make it a fairly faithful transformation into recursive descent parser. Yeah.
We're guaranteed that it's only at least one statement after the if. That's actually
That's right.
Essentially what I was getting at.
Exactly. Oh, yes. There will be only a,
I had
yeah.
an example last week where the tree had like a statement and then it did another if and it was still contained and it just confused me. So.
Yeah. So that's the dangling else problem.
Yeah.
Where.
That makes sense though because it's technically another statement immediately following it, right? So
Yes, exactly. So in this sense, if we have like, this is very confusing indentation, but if we have this, it really just means that the statement, well, it'd be easier if I could sort of wrap this, but the statement, the thing following our if and our, the parentheses, the expression, the right parenthesis, that has to be a statement. So we know whatever follows it must be a complete statement. So the only possible interpretation, according to our grammar, as long as we resolve the dangling else problem, is that this statement, this second if statement, so let me test y here. So the statement that tests y must be the body statement of the if statement that tests x. Does that make sense? So because, reading left to right, because we see this if keyword and an expression in parentheses, we know that the only thing that can possibly follow it is a statement. in either of these cases. So that means that this if statement, the Y testing if statement, must be a nested if statement of some kind. The dangling else problem in this grammar is ambiguous because that else could be part of this production. Oh, well, okay, it could be part of this production, the production of the if that tests X, or it can be the production of the if that tests Y. It can be either of those because of the dangling else problem, this ambiguity. We resolve the dangling else problem by whenever we are here inside of our parser, whenever we're here after the statement, if we see an else, we don't return. We don't return. We do the opposite. Oh, yeah. Once we return from statement. So we've seen if L paren expression, R paren statement, we can't tell which production we're in. So we resolve this ambiguity by just saying, if the next thing is an else, just always read that else. And what ends up happening is if we see an else, and we can never be inside of this production when we see an else following it. You see what I'm saying? So if we thought, okay, we're in this production, but I see an else next, we resolve the ambiguity by saying, if we see an else when we see this prefix, we must have been in this, we must be in this production. Questions on that? Should I repeat that again? Yeah.
So then if it isn't an else, then will we just basically undo our work essentially?
No, that's because it's a look ahead. So for all of these things, you have one look ahead to check. So if it's not an else, then we know it must be this production, if it's not an else. And if there's if it's nested, 10 levels deep, and it turns out that there's some syntax error on some parent if statement, it doesn't matter at this level, in this production. This is the way that this recursive description of language works. It's just like recursion. We only worry about the recursive step we're working on at that moment. And as long as that's correct, it composes with whatever is being called around it, whatever recursive function calls are being made around it. It doesn't matter. They just compose together. So as long as if the nested production works, if the outer production doesn't work, who cares? It's not the problem of the nested production's recursive call to handle that. Okay, so I think that's a good question. It's a good question. I don't know how much. So I went into the dangling else, but I didn't really go into the compound statement very much. So that'll give you a little insight into C, when you're actually programming in C, why it looks like that. So to put a little ideology back into this, I kind of was encouraged by my advisor in grad school to just always put curly braces. And there is some good evidence for the reason for this. Let's see if I can find this bug. There's kind of a good reason to do this. Let's see, is this why? I'm trying to remember if this is an example for this. Oh yeah, here's a fantastic example of why. So I can't prove that you should do this, but this is a really good example of why you should just always put curly braces. Don't try to be tricky with saving a single line. Can anyone see the problem here?
Yeah. It's always going to go to fail.
What's always going to go to fail?
That first, so with the thing you highlighted, that first go to fail applies to that if, but that second go to fail doesn't apply to anything. So it's just going to run.
Well, and to put it into syntax terms, this go to fail is the statement of the if production, this if syntax. Even though the programmer put some white space, but we now know that white space is just completely ignored, even though they put this white space, this go to fail is like a sibling of the if statement. And if we were to draw the tree of this, the second go to fail would just be a sibling of the if statement. So there's this long sequence of statements. Each one of them is, they're not nested. Each one of them is a sibling. If we imagine this as a list of statements, this is in our kind of simplified version of this grammar. These are all part of some compound statement. That's why we can have a list of them. These are all part of this statement star. And for each of these if statements, the if condition and the go-to fail statement is a complete match for one of these productions, or one of these productions. Make sense? Similarly, this if statement is a match for a complete if production. Questions on this? You see this? Anyone not see this? So what that means is that this next go-to fail is just another statement after the if statement, even though it's indented. Remember, indenting does not matter. So as your classmate was getting at, this go-to fail will always be executed. It's unconditionally executed. And what that means for security is that this check here, which makes sure your, I think, SSL certificate when you're visiting an HTTPS site, make sure that that SSL cert is actually authenticated. That means that any HTTPS site you go to, somebody can just make their own certificate. I can just say, hey, I'm Google. Here's my certificate. So, encryption doesn't really matter if the other person on the other end you're encrypting to like someone you don't want to see it. It's called a man-in-the-middle attack. So if you have the most amount of encryption in the world, doesn't really matter if you're speaking to me, if you're speaking to the attacker, it doesn't matter. So this can allow attackers to this will like basically circumvent the authentication. I think I actually didn't look too much in detail, but I think that's the gist of it. Let's see what they say. Privileged network position. Okay, yeah. See, they're saying it's a man-in-the-middle attack. So I'm pretty sure that's what's going on here. Yeah, so that's a really funny one. So why I say always put curly braces is so I don't know how this happened. We'd have to look at like the version control system to actually see, which is why you have version control, so you can blame the people who did this. No, I mean everybody makes mistakes when they code, but maybe they tried to delete one of these if statements, but they forgot about the body of it. If there were curly braces, you would have had some leftover curly brace afterwards. You would have gotten a syntax error. If they were trying to add a go-to fail here and didn't realize there already was one, and there were curly braces, you wouldn't have had this problem. You would have just had some dead code here. This go-to fail wouldn't have been reachable. If there was a curly brace around this if statement, the second go-to fail wouldn't have been reachable, right? Because it's after a previous go-to fail. So this is actually a good case. I got to remember this case for next time when I teach this, because this is a really good case of why syntax kind of like matters. Okay, questions? Any other questions on this? Okay, so that's project 3. Go over the last couple lectures to kind of get more on the semantics of this grammar, the order of operations, the fact that we have types for each of these operators, how you do type. Well, we don't. You can do type checking as a bonus exercise, but you can assume that I'm not going to give you examples where one operator will have the wrong types. So I'm not going to give you plus an int and a boolean, because LLVM is actually typed. And if you wanted to support that, you'd have to actually reject programs that do this. But I won't give you these. I won't give you these kinds of type errors. We looked at compare and branch instructions. So this was the stuff from last time, where for compare, we have this instruction. And yeah, just for review, so compare takes 2 operands of whatever type you tell it. So in this case, I32, and always returns a single bit integer. Yeah.
When I was going to project 3, I saw that in the while loop is just if statement, but without unconditional branch.
Yeah.
I'm actually confused because if statement has a branch.
Right.
Well, how does an unconditional branch,
with an extra unconditional branch, with an extra branch.
How does it actually look like in the code?
We'll do that today. We'll go over, so we'll show the sort of templates for making these, for implementing each of these simple C language constructs, including the while loop. Okay, so this integer compare operation takes 2 integers of whatever type you want to give it. For us, all integers are 32-bit, and it always returns a 1-bit integer, which corresponds to a Boolean value. That was compare, and that's how you would implement the equalities and inequalities, the integer inequalities and equalities. And then we had the Boolean instructions and OR, and we use XOR for not because there's no unary negation in LLVM. And these work just like arithmetic, except they're operating on 1-bit integers. So this is kind of review. Questions on this? Any questions on this? So you can review the lectures, review the slides for those operations. But the code generation is going to work just like it works for any other expression code generation. You can just make new expression functions. Then we looked at the LLVM's branch instructions. So the branch always takes a 1-bit value, which we can get from a comparison operation or the result of an AND and an OR. And the conditional branch in LLVM takes the condition value or some register and 2 labels. The first label is the next instruction that will be executed if the condition is true. The second label is the instruction that will be executed if the condition is false. So very much exactly what you need for implementing an if statement. And a lot more convenient syntax than writing in like Intel assembly, for instance. So questions on this? Questions on this? This is what the branch statement looks like. So today, we're going to look at how we can actually generate code for our simple C constructs. All right, here's our if statement. And recall that we can represent this structured, these structured branching constructs using these flowcharts. So wherever we have some body of an if statement, we can turn that into a block. And any of the what's called straight line code that doesn't have any branching in or out of it, we can put those in a single block in this flowchart. And whenever there's a comparison, like this x equals 10, that signifies a point at which you have some mutually exclusive choice about where to go next in the program. So just like you know when you actually implement your own code, if you put an if statement here, the body will only be executed once if you evaluate this expression, if it evaluates to true, non-zero. So that can be reflected in this flowchart where the next instruction following this sequence of instructions, this straight line sequence of instructions, depends on the condition. If it's yes, then we go to this other block or sequence of instructions. Otherwise, we go to the sequence instructions after the if statement. Questions on this? This is all kind of review. All good? Okay. So the template for an if statement in LLVM, there are, of course, multiple ways to do this. This is kind of the most sort of naive and simple way to do it, is you first generate code for the conditional expression. And there's going to be some final step in that conditional expression. Maybe it's an I compare, maybe it's an and, maybe it's an or. There's going to be some last step in your expression. And that's just all handled by the expression code generator, parser and code generator. So all of this, let me get that. So all of this code is generated by a recursive call to the expression parser and code generator. And then your generator for the statement, for the if statement, will always emit some branch, then emit the label for the if body, and then just recursively generate code for the statement. Once that's done, it'll generate an unconditional branch to a label that represents the code after the if statement. So this print 0 is the code after the if statement. This print x is the code inside the if body, and the stuff before it. And the conditional expression is all the code before we emit this branch. So questions on this? Anything look unnecessary or redundant here? Yeah.
So my question is, do you have to put out if body generate code for the statement, or is that a comment on that?
This is a comment. This is an LLVM comment.
It's not real code, right?
Well, this is real code. It's just commented. I mean, I didn't emit the code here. So this is kind of, you think of this as like a template. The stuff in red is like the template. This is what gets generated when you have an if statement.
Okay.
So yeah, go ahead.
And if body is just, you're just using it to show us that that's the body statement, pretty much.
Yeah, that's what's in the syntax of simple C. The statement child of our if statement can just be whatever code you generate there. You just plug it in as if this is like a template.
So we don't have to do that when we do projects. Like we don't have to say generate code for a statement and do it. We can just say branch label start %.
Yeah, you don't literally have to write all these comments.
Yeah.
And no, you don't have to do that. But they're comments, they're white space in LLVM's language. So
Okay.
yeah. Yep. Yeah. So I compare. So any of these Boolean operations. So remember the types of all these Boolean operations is always returns a bool. So as long as that's the last instruction that you run, then you're good to go. You're going to have an integer of 1 bit. So like I sort of belabored last time, when if we actually wanted to prevent programs that mixed integers and booleans in the same operation, we'd have to write a type checker to guarantee that didn't happen. But I won't give you those, and it's left as a bonus exercise to do that type checking while you generate code. Okay, that's not a question. Okay, so what's kind of interesting about this, to me anyway, is that even if you have this hugely complicated if statement, because the work of generating code for statements is done somewhere else, it's done by this statement parser, the actual code that gets generated for an if statement is really pretty small. It's just branches and labels. The if statement itself doesn't actually generate any of the instructions that compute anything. It just corresponds to a branch statement, and the labels aren't computing anything. They're just references to other parts of the code. Does that make sense? Yeah.
Why does it need to be our label 14?
The 4 this one?
Oh.
Why do we need this one? So that's a really good question. We've got an unconditional branch here that jumps to the next line.
Yeah.
And you could certainly optimize this way. LLVM will probably optimize it away for you. But one reason to do this, so I sort of like starting with correctness rather than optimality. So I try to make things sort of naively implemented, a very naive template, and optimize later. And actually, because you could generate either an if, you may not know ahead of time whether you have an else statement here. Or you could write the code to optimize this way. But if I just wanted to be kind of lazy and correct, I would say, well, I'm not going to assume anything about an else statement. I'm just going to say, whenever there's an if statement here, I'll just always, use this as, I'll always put an unconditional branch after it, and then just manipulate the labels if I have an else statement. I mean, yeah. So you feel free to do however you like, add optimization. I like to get correctness first and kind of optimize later. Yeah.
Will the LLVM optimize out the unnecessary break statement?
Yeah, it will. I'm pretty sure it will. Yeah. So if you were to generate code for this, shall we see? Shall we look? Sound good? All right. Let's see if we can see if LLVM will optimize this away. So I can't remember what this optimization would be called, but I should do it. I guess this is one of the people optimizations. So let's see if I can get it to create the unoptimized version. Gotta remember the command line syntax here. Turn off optimization. And just a warning, that's okay. So let's see what we got here. Okay, so this, indeed, the front end for C here will actually do this kind of unnecessary branch because it's just really simple to be, when it's simple, it's easier to be correct. And then you automate the optimization later. You let the compiler do the optimization. Okay, so we've seen that LLVM, the Clang front end, the C compiler that's shipped with the, it's called Clang, that's shipped as part of the LLVM project, will generate this sort of unoptimal LLVM code. And if we use LLVM to compile it to assembly, I think this will compile it to assembly. Now I've got assembly, and let's see if it's gone. I think it is. So here is the here's the compare. So here's a compare, right? That's the compare. Here's the branch. So if that comparison doesn't hold, it skips the body of the loop. So this is the body of the this is the body. There's our printf. You can see that's the body of our function. Here's the kind of prologue and the part that computes the comparison and does the branch. And notice that between the body of the if statement and the subsequent code, there's no jump. So LLVM will handle that for you. It'll just remove any kind of superfluous jumps you have. And I think those are some of the earliest optimizations that the compiler does. I think this is handled by the people optimizer as well. They'll look at there's just a bunch of basically heuristic optimizations where you look at a window of 3 or 4 instructions and say, oh, do I have a branch to the next statement? Remove it. Do I have a couple multiplications in a row? Can I turn that into a single multiplication? Things like that. So yes, indeed, LLVM removes that superfluous branch. And that's actually one of the benefits of generating code to this intermediate language, because we can just make it simple and correct without having to worry about it, and just reuse all the optimizations that the brilliant LLVM developers have developed over the years. Okay, that's a good question. Other questions? Other questions about this? Okay, so that's why I kind of recommend just doing it in a kind of mindless, simple way. Oh yeah, so another thing, just like the body of the if statement is handled by a piece of the parser that you've already written, you don't have to go out and rewrite how statements are generated. You also don't have to worry about how the expression code is generated. You already have code that will generate an expression. You just need to remember which temporary variable the result of that expression's computation is stored in. And if you've written this in the recursive descent style, then expression will already just return a temporary variable, or perhaps a number if you've done some optimization. Yeah, so we get this temporary variable, and that just plugs right into our template for calling this branch instruction. Okay, questions on this? Everybody, we're all on the same page? Okay. So this is pseudocode for parsing and generating code for if statements. Here's I call it an if statement. You're free to organize it however you like. If you want to put it all the statements in one function. We're going to consume the if keyword. We're going to consume the lparen token. And then after that, we've got to read the expression. What does expression return?
I believe it'll return the t value.
Yeah, it's going to return a temporary register, the name of a temporary register. But it's not going to actually compute the expression. It's going to return an LLVM register that will hold the value at runtime when this program is run. Or if you're doing optimization, it might return a value like true or false. So this is just a literal. If we look at if lparen, all the stuff in black, that's just a literal transformation of our grammar. So remember, our grammar just looks like this. And our code generation, our pseudocode for code generation, is literally just a transformation from the grammar to some code. I mean, depending on how you wrote your parser, you may have, maybe you're having to do some look ahead, you have to do some other bookkeeping. But roughly speaking, we can just turn that production into code, and that's the code in black. And as I've said before, I strongly recommend getting the parsing working correctly first. If the parsing's not working, the code generation is absolutely not going to work. So make sure the parsing is working 100% correct before starting to add the code generation stuff. And so now the code generation for the pseudocode works like this. We create a couple of new labels, one for the body and one for the end. And then we emit our branch. And remember from our template that our branch has the LLVM register holding the condition and two labels. The first label is the code that you want to run if the branch is true. Otherwise, the code that you want to run if the branch is false, or if the condition is false. So we just emit that branch, plugging in the condition register, plugging in the label of the body and the label for what's after the if statement. Then we just emit a label, an LLVM label, which is the name of the label followed by a colon. Then in following with our template, after we have the label representing the body, we just generate whatever the code for the statement is. How do we generate the code for the statement? We just call the statement parser. And then finally, we generate a label for the code that's after the if statement. So notice here that alone, this function isn't valid LLVM because it just ends with this label and no instruction. But when you compose it with other stuff, whatever happens to get run after this if statement, maybe it has, once it goes back to its parent, that will start emitting code, and whatever code gets emitted after, whatever is next after the if statement, that code will be labeled with this end label that the if statement code generator produced. And just sort of, I sort of hand wave this emit function, but I just list together a bunch of strings and variables. So it's a little hard to parse, but I wanted to fit it on the slide. So it's this is the static string. You could use string formatting. That would also be good. Followed by whatever the conditional label is, followed by a string that just has a comma and the label keyword. Because remember that branches need to have the label keyword to tell that this register is actually a code address, and so on. And same thing with the label itself. So the label is just the name of the label followed by a colon. So questions on this? Questions on this pseudocode? Okay. Yeah, and I just wanted to point out that the order that you do these emits and call these statement, that order matters because we want to make sure that this label is labeling the body of the function. So the order here matters for this. Okay, so what about these labels? So labels are really just another kind of LLVM register. You can think of them like that, except they happen to store the address in code. Now, when it generates assembly, the actual physical address of that code in memory is not actually really determined necessarily, is not necessarily going to be determined by the compiler. The linker is going to figure out where to put the code in the final binary. But LLVM kind of has its own, treats these as if they're something like an address of code. And because they look exactly like a temporary register, you're free to generate them however you like. You can use your same temporary register generator. If you want the output code to look a little more readable, you can call them labels, you can call them if branches or else branches. You're free to do however you like. But the simplest is you can just use the same temporary register labeling that you used for other temporary registers. So questions on that? That's pretty clear, right? Okay, so let's look at the rest of the constructs that we have. So they're only, marginally more complicated than the regular if statement. So here's a little review of the flow chart for if then else statements. They're very much like if statements, except once our condition happens to be false, there's an extra body of mutually exclusive code here. So in one run of this program, it will either go to the S branch and return to the same code that's after our if statement, or it'll go to the no branch. But no matter which path we take, it'll always end up here after our if statement. That's why we have this 2 in edges to this block. If you think of this as a DAG, this block that appears after the if statement has 2 in edges. Yeah.
How would this be different in LLVM if you just have the if statement and then anything?
It's a good question. What would the LLVM look? How would the LLVM look? It would look a little different. Not too different, but a little bit different. So just like before, we have the code for conditional expressions being generated and returned into some temporary register like T2. Just like before, we generate a branch. But this time, the labels of that branch, it still needs to take 2 labels. One for when the condition is true, which is this, and one for when the condition is false. But in this case, the semantics of this if statement are these 2 blocks are mutually exclusive. And the first block is run when the condition is true. The second block is run when the condition is true, but not both. And of course, once they finish, we start executing print x. So the way we represent that in LLVM, this branch, because it takes 2 labels, makes it very convenient to do this. The first label is just like before, is the if body, the body of the if. The second label, instead of being the code after the if statement, it's the code for the else body instead. So it works just like the if statement, except now instead of jumping immediately to the end block, we jump to the else block. Make sense? What's that?
Yeah,
Answer your question? Okay, great. Okay, so I think that's fairly straightforward. Let's look at what the pseudocode for this would look like. So just like before, all of the code in black text here is just a transliteration of our grammar. Let's look at our grammar again, just to review. So remember, the grammar is just the if terminal, followed by the lparen terminal, followed by expression, followed by the rparen terminal, followed by a statement, now followed by an else terminal, followed by yet another statement. So just like before, we don't have to worry at all about how to generate code for a statement or what it looks like. We just offload that to one of our recursive functions and assume that it works properly. Okay, so to generate code for this, it's slightly different. We still need 2 labels for our branch, but in this case, it's going to be jumping to the body of the if and one that jumps to the else. And then in order to handle this behavior where whichever block we take, they always branch back to the same instructions that follow the if statement. In order to make sure we have this behavior, we add a label before the code after our if statement. So whatever code happens to come after the if statement, we have to give that its own label so that the if body and the else body can jump to it. So that's reflected here, where we generate 3 new labels, one for the if body, one for the else body, and one for the code after the if statement. Yeah. No problem.
In your pseudocode,
Yeah.
how do you do the left curly and right curly?
Aha. The left.
You just looking at the conditions that have to.
So recall that this is just another kind of statement, like we talked about in the beginning of class. This L curly and right curly is just another kind of statement. So when you recursively call statement, that recursive call will handle whatever kind of statement it is, whether it's a compound statement or any other kind of statement. So that's why the code generation for if statements is actually fairly simple. We don't have to consider what nested statements are inside of if. We use this context-free definition of language to express the recursive nature of language and just say, we know it's going to be some kind of statement. We don't care what kind of statement. So we just call statement. And if it's, yeah, it makes it very simple, right? It makes it very simple to do this. So that's why I'm saying, like, you know, don't get too clever when writing this. You can it's much better to get this correct and simple first. And then, you know, this is how you can see this is even how industrial strength compilers work. The Clang front end doesn't bother trying to be clever about this. It tries to be correct and simple. And then this whole machinery for optimization will make it then fast and do it in an automated way, because it's very tedious for humans to do. Now, compilers can outperform a lot of people, probably me, but when it comes to like some very special purpose, maybe graphics card programming, hand compiled assembly can still outperform compiled assembly in some cases. But yeah, so yeah, just be simple. And because we define our language like this, where the curly braces is just another kind of statement, we don't have to do any of that reasoning when we're processing an if statement. And this is kind of the beauty of this recursion and this recursive descent, is that if you only have to reason about each recursive function by itself, and define what its inputs and outputs are. And then if you get that right, they'll all just kind of fit together like Lego blocks. They'll all just compose together. Now, the if getting it right is, that's the tricky part. But once you start practicing these recursive algorithms, and you'll probably have these in like interviews and stuff. Once you start practicing these recursive algorithms, that'll become much easier to reason about. You'll sort of, always think about the recursive step and then the base case, and think about how all the multiple calls work together. All right, but yeah, good question. It's good to review this. Okay, so as I was saying before, the black is just our grammar. We need to generate 3 labels, one for the if body, one for the else body, one for the end. Then just like before, we emit our branch, except instead of jumping to either branching to the if body or to the end label, we branch to the else body. And then we just emit labels before we emit each of the code for the statements. So we emit the label for our if body, emit the code for the statement, because when you call statement, that's going to emit all the code that you need for that statement. We're going to consume this else token here, emit the label for our else body, and then just recursively call the statement function that emits code for whatever happens to be the contents of the else branch. And finally, just like before, we emit a label representing the next instruction after the if statement. So one thing that I didn't kind of show here is that, when we talked about it a little bit, you have this common prefix between the 2 kinds of if statements. So I'm leaving it to you to resolve the dangling else, and you may have to combine this pseudocode a little bit. But it shouldn't be too bad. And what makes it a little simpler is if you always emit a label after the if, before you have an else, although, you could certainly optimize it away. You can just kind of wait until you see an else and then make a decision about what this label is, going to be. In fact, if you always make this the end label or always make this the same label, then you can always emit it here, and it'll always just work. Just whether you have an else or not at the end. So in other words, I'm not explaining this very clearly, but you can basically produce this, and then if you see an else branch, then this end it'll just already be the body of the else rather than the end. Anyway, write it, and you'll see what I mean when you write it. Yeah.
So on that, you just have like in the grammar, it's just like if left branch, statement, right branch, and then else on like different line. Like instead of like having if else, you just have if, and then one line of grammar for else. You just check either word.
So if I have something like if here.
So like in your grammar, right?
Yeah.
If left paren, expression right paren, statement.
Mm-hmm.
Could you just get rid of that second one and just have it like else left paren?
Oh, have else statement be its own statement?
Yeah. Could you
That's an interesting question. So could I have something? Well, okay. So if I wrote something like this, that would still be part of the language. I could also write something like this, right? So that would be part of the language, right? That would be valid. So the thing is, yeah. So that you would lift it to be its own statement. So else cannot appear unless, I mean, in the definition of our language, just like in C, else only makes sense when it's part of an if then else statement. So by itself, doesn't really mean much. You might interpret it as always run this. So you could do that. I mean, you could certainly design your language like that. You're free to do that. But yeah, C doesn't do that. But yeah, that would be the consequence of that. So I guess you're saying that would be resolving the dangling else. You'd be like, well, let's lift else to be its own. I mean, you would still need to know which if statement it matches. So you'd have, yeah, it would actually make it probably harder to write the parser. I think this is easy, probably easier to write.
You got only 14 minutes.
Oh, thanks. 15 minutes. Okay, let me just turn the brightness down. Okay, so that's a pseudocode for if statements. All right, now let's get to whiles, and then we'll do a quick example. All right, so the while statement. So as somebody asked in the beginning, a classmate asked, how is a while statement just an if statement with an unconditional branch? Well, what I meant by that is that if we ignore this branch, this jump right here, this edge, this looks exactly like an if statement, right? It's just some block followed by, or an if then else statement rather, followed by, more or less. It looks just like an if statement where you got one block with two separate branches coming out of that block. The difference is the body of the if statement has an unconditional branch back to the comparison expression or the conditional expression. That's what I meant by a while loop is basically an if statement with an unconditional branch. And this makes sense in the kind of intuitive semantics you have for while loops. This body will be executed however many times it takes before this condition is no longer true. So the way we implement that in LLVM, or any assembly language that has compare and branch only, is just like before, just like the if statement, we generate code for the conditional expression. We emit the branch itself. And in this case, just like an it's just an if statement, not an if then else. Just like an if statement, the label goes into the body of the if or the while, and the label or the false branch goes to the first statement after the while. So this section here is basically identical to an if statement. The difference is inside of the body there is this unconditional branch. So in LLVM, an unconditional branch just takes a single label and that's it. Just means it always jumps to that label. And where does it jump to? Well, it jumps to the start of the code that computes the conditional expression. So you can call this the head of the while loop. That is this code right here. It's not here, it's not this code. This code is outside of the while loop, but the code inside of the parentheses of the while loop, which kind of like is sort of syntactically says something about its proximity to the while loop. That code goes here inside of our head, and it has its own label so that we can unconditionally branch to it. That's how you implement a while loop at LLVM. So every time we do this comparison, if the branch is still true, we hit this unconditional branch. Forces the machine to do the comparison again, jumps back to the top, and so on. And this works because these low-level machines like LLVM, Intel, you can change the state of the registers or the state of the memory in this body, which will cause the head of the while loop to compute some different value, compute potentially a false value here. Questions on this? So yeah, just basically an if statement with this extra unconditional branch. And the pseudocode reflects that. So again, we've got in black text here, we've got the grammar for a while loop. So if we take a look at our while loop here, we've got the grammar. We've got the grammar for the while loop. So it's just a while keyword, followed by lparen, followed by expression, followed by rparen, followed by a single statement. Notice it's basically identical syntax to the if statement. It's almost identical, except the keyword is different. So the keyword allows us, the compiler writer, to, just tells us to generate a different piece of code. So that's in black, that's our production. So because we want to be able to jump back and recompute the expression, we generate a new label before we generate code for the expression. So just a little reminder, this code, this initial block, is not part of the while loop. It won't even be visible once we start parsing the while statement. The while statement is a sibling to those instructions. So we emit this label, we emit the code for generating an expression, and continue on with the tokens. And then just like we do for an if statement, we create two labels, one for the body of the while loop, one for the code that follows the while loop. We emit the branch, just like we did before. We emit a label for the body. We recursively call statement to produce the code for the statement. And then, so I've highlighted in purple the differences between an if statement. Here is where we put our unconditional branch. At the end of the body, but before the end label. The end label represents the code after the while loop. So we want to make sure we branch. We don't want to branch after that. We want to branch before we hit that end. So if this branch is false, we jump to the end label. We no longer have this unconditional branch anymore. Questions on this? Pretty straightforward, right? And so now that you've already built up the rest of your parser with statement and expression, this just plugs right in to these code generators for control flow.